Hello and welcome back. In 3.1, we get to work with the constant E and compound interest. Darken that eye in a little bit. Okay, E and compound interest. So we've touched on this a little bit in Chapter 1. In Chapter 3, we get to take a little bit more of a detailed examination. So we're going to now define E using limits. So E is going to be the limit as n approaches infinity of 1 plus 1 over n to the n power. Now to make this a little bit easier for you to do on the calculator, we're going to let f of x equal 1 plus 1 over x to the x power. And I'm going to have you try out various values of x. So I'll try out a 1, a 10, a 100, 1,000, and a 1,000,000. We'll run through the 1 together. So then f of x is our 1 plus 1 over x quantity to the x power. So f of 1 plus 1 over 1 is 2. 2 to the first is just 2. Let me have you try out, go ahead and pause it, try out these next 4 and see what values you come up with. Okay, welcome back. So f of 10, 1 plus a 10th, quantity raised to the 10th power. Yeah, 2.59, that's a likely 9 there, 374,246. F of 100, similar idea, only now all of our x's are 100s. So 1 plus a 100, 1 over 100 raised to the 100th power. And there we're at about 2.704813829. For the input of 1,000, 1 plus 1 1,000th to the 1,000th power. Now we're at about 2.716923932. And a million, f of a million. So 1 plus 1 1,000,000th to the 1,000,000th power. Room there, that is about 2.718280469. I took the liberty of also trying out a billion. Giving us approximately 2.718281827. So notice we're not just growing without bounds, we sort of seem to be converting to a number that's about 2.718. In fact, we're precise fairly far out on here. The number E is much like pi, an irrational number. It goes on forever without terminating or repeating. So let's see where that applies to these compound interest problems. And to start with more with the concept, we'll look at simple interest first and build the compound. So like in chapter 1, reminder, P is principal, R is the rate. Make sure we go to decimal form. T is the time, and the units of time should match the rate as well. So if it's weekly interest, time should be in weeks, things like that. All right, so our new amount would be the initial amount plus principal times rate times time. This would be the interest. If we do that as compound interest, however, now we're getting paid interest not just on our principal, but also on the interest payments that the bank made on our behalf. And we'll do n times per year. That's where we get our P. A is P by 1 plus R over N to the NT that we saw back in chapter 1. And if you want to see just not a complete proof of this, but sort of a derivation, if we do the number of compoundings as 0, our amount in the bank is just P. Just the principal that we put in. First compounding is P plus P times R over N. So if it's just to use clean numbers, not that you'd see an interest rate like this, but 12% interest compounded monthly, 1% each month then. So you're getting not the full interest rate each time, you're getting that split out among however many compoundings. We can do a little bit of factoring on that, and we have P times 1 plus R over N. So that's our new account balance. So when we do our second compounding, our account has what we had before, which is our P by 1 plus R over N, plus then we'll get paid interest, R over N of it, based on our previous balance. And notice we have this P by 1 plus R over N in both of these. We can still factor that. So our first term, we're left with a 1. Our second term, we're left with an R over N. So then we have P by 1 plus R over N squared. We had 2 copies of that, and that will continue happening. The fifth would be P 1 plus R over N to the fifth, etc., etc., etc. So that's sort of how we come about having this. It's based on just sort of building off of this. One little reminder in this book, daily will mean 365. The banker's rule that most banks typically use and a lot of other textbooks would use, they use the fiction that N is 360 for that. This author uses the 365, the correct number of days in a year, even though, as I said, the bankers pretend that there's 360 days in a year. So the idea of continuously compounding the interest, we go from compounding it yearly, monthly, weekly, daily, hourly. the number of compoundings goes to infinity. So we look at what happens as n goes to infinity of this p by 1 plus r over n to the n times t. Well, p is a factor by itself, not affected by n. We can pull that to the front. So we now have p times the limit as n goes to infinity of 1 plus r over n to the n t power. Then we do a little bit of substitution. Put in a placeholder variable. Let u equal n divided by r. If n's going to infinity, what's happening with u? So n is growing without bounds. R is a rate, so it's an interest rate. We're going to enter it as a positive. Hopefully you see that u would also then be approaching infinity. So if u is n over r, then the reciprocal r over n is the reciprocal of u. So then a little bit of substitution. We now have p times the limit as u approaches infinity. 1 plus, now I have that r over n. That is the same as 1 over u. Raised to the n by itself would be u times r. So just solve this thing for n. And we're going to just use a little property of exponents here. Limit as u goes to infinity. We'll call this 1 plus 1 over u to the u raised to the RT power. Power raised to a power. Our shortcut is to multiply. Hopefully you recognize this much of it. Let me just kind of highlight it. This much of it. Hopefully you recognize that as u goes to infinity. That is our definition for e that we saw at the beginning of the section. So now we have p times e to the RT. That's where that formula came from that they had us just sort of use in chapter 1, and that's our new account balance. So this is if we have continuous interest. So now we can use some of our properties of exponents and logarithms, which we covered after the interest problems before. Exponents and logarithms to work on time for these. So we want to know how long will it take for a $2,000 investment to reach $2,500. And what did I pick? 2%. I ran it through, my apologies, with 3%. 3% compounded continuously. So before, our goal was just to get get the amount, and it was just sort of a plug and chug. We didn't have to do any solving. Now we have to do at least just a little bit of work, not a terrible amount. Compounded continuously, we're following the a is p e to the RT power. 2,000 is our initial investment. That is the principal. E is just always going to be there for a continuously compounded problem. Rate 3% in decimal form, 0.03. We don't know the time they asked us how long. That stays a variable. And our goal, we know the new amount we want, 2,500. So then after that, we'll just divide both sides by 2,000. So 25 20ths will turn into 5 fourths. So 5 fourths is e to the 0.03 times t. So we'll take the natural log of both sides. Natural log of 5 fourths is natural log of e to the 0.03t. So natural log of 5 fourths is worth 0.03 times t. So that exponent became a factor times the natural log of e. Natural log of e, though, recall, is 1. If you need a little reminder why that is, what natural log of e equal, let's see, we haven't used an x on here. So then e, the base of the natural log raised to the x power, is worth e. Bases are the same and not worth 1 or negative numbers, so the exponents have to be the same. So x is worth 1 there. So that's a little reminder if you need a little help with why that's true, and in general, log base b of b is going to be a 1. So now we have natural log of 5 fourths is worth 3/10, or 300, sorry, 300ths of t. So t is natural log of 5 fourths divided by 300ths. Quick note on here, the 300ths in the denominator, not part of the argument of the natural logarithm. This is not the same as natural log of 5 over 4 over 0.03. Totally separate. Natural log is in the top only here. And since this is a word problem, we would plug that in and get a quick decimal approximation. So as far as keying it in, let's see if I can get a decent angle where you can see it on there. So natural log of 5 over 4. So notice the calculator kind of opens a parenthesis for me there. Close it up, then divide by 300ths. And then we'll round that. So that approximately 7.438, so we'll call it 7.44 years. So that just goes into our answer sentence. So our units this time are years. 7.44 years to reach $2,500. Alright, so this one I'm going to encourage you to pause the video and try on your own. How long will it take you to double an investment at 4% continuously compounded interest? So if you're going to pause it, go ahead and pause it. Okay, welcome back. So we invested P dollars. We have e raised to the r 0.04 times t. We don't know the time. We want to double our investment. We invested P dollars, so if we double that, that's just 2p. So you might have noticed at the beginning of the problem, I didn't tell you how much money you invested in this. For doubling time, it turns out it doesn't matter how much you invested. As long as, of course, the bank doesn't have some type of rules about a minimum balance for that type of account. in that case, then they may start charging you different fees and things like that, change the calculations. But assuming that you follow all the minimum balance rules, it doesn't really matter mathematically what your initial investment was. So it would take me the same amount of time to double at 4% my investment of $100 as it would take a billionaire to double their investment of $20 million. It'll double at the same rate for both of us, as long as we're looking at the same interest rate. So the P, notice, cancels out entirely. So then 2 is e to the 0.04 times t. Just like before, then natural log of both sides. So natural log of 2 is natural log of e to the 400ths times t. Natural log of 2 then, log of something to a power. The power can become a factor, so we pull that 0.04t. And we have natural log of e, which again is 1. So natural log of 2 is 400ths of t, and this is now just a linear equation. So divide by 400ths on both sides. So t is natural log 2 divided by 400ths. And then we're just plugging and chugging it, approximating it on the calculator. So natural log 2, close it up, divide by 0.04. So about 17.3286791. So we'll just go to the thousandths and decide what to do with the hundredths. So this will be 33. So it will take 17.33 years to double the investment. All right, so let me give you all some problems to play with in this one. Again, some of this we've worked with a little bit in chapter 1. Some of that, the derivation of E, deriving where the continuous compounded interest formula comes from, that's the new stuff, and this doubling time, working with the logarithms as well as the exponentials together in one problem. So in 3.1, I would recommend 1 through 37 on the odds, 43 to 49 also on the odds. And of course, if you have any questions, please get in touch with me. Otherwise, I will see you next time. Stay safe out there.